Okay, we're back to doing some videos on these things. We're in chapter 8. At some point in time we'll go back and get chapter 7 so you can have some fun with it. But right now we're in chapter 8, and chapter 8 gets into right triangles and trigonometry. So we're going to take right triangles and turn them every which way but loose. First thing we're going to do is a very simple concept that can be used in multiple ways. And so we're going to introduce a concept. It's called the geometric mean. What we're going to do is we're going to very simply introduce this concept. There'll be another section in this video and segment that you'll be able to go to if you'd like to really find the real meaning of geometric mean and what it means and how we relate that to arithmetic mean. And a little dissertation on that and a derivation of what it means as far as central tendencies and statistics. But for geometry, we're going to look at this right now. Now, the term geometric does not really have anything to do with geometry, even though it starts with geo. The term geometric in math simply means we're looking at products of numbers, and the term arithmetic means that we're looking at the addition or the sum of numbers. So what this means is geometric mean is we're looking at a type of average that is produced, created by the product of numbers or statistics or a measure of central tendency that is produced by a product of numbers. That's a lot of highfalutin stuff on something that's pretty simple. Geometric mean definition. The geometric mean between, this is the definition we're going to use, the geometric mean between two numbers is the positive square root of their product. Okay? We're going to call that GM. When you see GM in this chapter, we'll be talking about geometric mean. Now, an example of this definition, worded definition, is between any two numbers is the positive square root of their product. Geometric mean of 4 and 9 is the square root of the positive square root of their product. So we multiply 4 times 9, so that's the square root of 36, which is 6. That's all it is. Now we're looking at the positive square root because when we talk about geometric mean in geometry, we're going to be looking at distances. And as you have been told from way, way, way back when we talked about distances way back in chapter 1, is that distances in geometry for our purposes right now are measured in positive numbers, not negative. We're not sure what a negative number is. Now, when you get to vectors, in our classes we'll get into vectors, and when you get into vectors in physics and in other places, then what you'll look at is you'll look at what a negative distance means, and that will begin to take on meaning. But right now we're looking at positive numbers because distance is positive. So geometric mean between 4 and 9 is square root of 4 times 9, square root of 36 equals 6. Geometric mean of 6 and 15 is the square root of 6 times 15, which is the square root of 90, which is about 9.5. And geometric mean between 5 and 20 is the square root of 5 times 20 equals the square root of 100, or equals the square root of 10. Very simple way to do it. Next, we're going to introduce a couple of theorems and show you how to use this concept of geometric mean to actually solve for some distances and some segment relationships on right triangles. Okay, the first theorem we're going to look at is theorem 8.1. Now, I have titled this, and it's given it a little nickname here, of the right triangle, right angle, altitude theorem. Long name to mean a lot of nothing. What you've got is you've got a right triangle. So we have a right triangle XYZ. Now, what we're going to do is, at the right angle, we're going to drop an altitude. So at the right angle, we're going to form an altitude. That altitude is YW. Notice it is perpendicular to the hypotenuse of triangle XYZ. Okay? Now when you drop that altitude from the right angle to the hypotenuse, you actually create 3 similar triangles. Okay? The first triangle, XYZ, is the big triangle. The second triangle, XWY, is what I call the middle or the medium triangle. Okay? And the last triangle, YWZ, is the small triangle. Okay? And this is how they're put together. On the big and the medium one, X goes to X, Y goes to W, and Z goes to Y. Okay? This is how they're set up. So basically, if we were to set these up like so, we'd come over here, we'd say X, Y, Z, and then the second one, okay, would be X, W, Y, and the last one would go like this. Alright, so if we were to set those up, this is what they look like. This right here is a large, okay, right there. This one right here is a medium. And this one right here would be the small. Okay? So what we've got is we have three triangles. When we drop this altitude from the right angle to the hypotenuse, create that, we're going to create three similar triangles. We've been talking about similar triangles. Did that in chapter 7. We talked about ratios and similar triangles and what all that meant. And now we're going to use that in finding these, and we're going to use this with this geometric mean to determine what some distances are between all these three triangles. Now, this concept is extremely useful in construction of all kinds, in engineering, mechanical engineering, civil engineering, construction and buildings, and all that, is the ability to find these distances. I've used it also in orienteering to find distances across places, creek, canyon, and obstacles that we had to cross. And basically what we've got is a large triangle that is similar to a medium triangle that is similar to a small. Three congruent triangles simply by dropping that altitude from the right angle to the hypotenuse. Okay? And we'll look at some samples of how to solve some problems with this. Now, this theorem, Theorem 8.2, I call it the right triangle GM theorem number 1, because there's a couple of them. Right triangle geometric mean theorem number 1. We have a right triangle where we've dropped an altitude from the right angle to the hypotenuse. We have right triangle LMN with an altitude of MJ. The measure of the altitude is the GM, geometric mean, of the measure of the two segments created on the hypotenuse. This GM of the measures of the two segments, let's get that corrected so we got it right. Measures of the two segments created on the hypotenuse. Okay? Alright, what does that mean? The measure of the altitude, in other words, the length of MJ equals, is the GM, okay, geometric mean of the measures, okay, right, and the GM is the square root of the product of these two numbers. So, the length of LJ and the length of JN. So basically we can just take those two lengths, multiply them by each other, and take the square root, and we can find what the altitude is. Okay? And we're going to show this a little later on in a much easier thing, but this is a concept of what we're going to be doing. Okay? Now what we're going to be doing is getting into some sample problems and see if we can look at how this works.